Hey everybody, welcome back to Info 3370, studying social inequality with data science. In this lesson, we're beginning our tour through machine learning. Before we begin with particular estimators, I'd like to remind you that at a high level, machine learning is just an extension of statistics. Many of the basics are the same, so we are going to still learn from training data, evaluate and test data to pick the approach that seems to be performing the best, and then predict for new cases. The difference here is just that machine learning is a much broader toolkit, so you'll have a larger set of possible prediction functions to draw on when searching for the best way to make predictions for an outcome given a set of predictors. Here we're focused on supervised machine learning, and you'll have to go elsewhere to get resources on unsupervised machine learning, which is a different kind of machine learning. Today we'll discuss regularized regression. Regularized regression is an excellent starting point because in many ways it's just the same as ordinary least squares. The motivation is simple. If you have lots of predictors available to you, you might be tempted to include them all in your model to predict the outcome. You might also think that some of those predictors are related to the outcome in ways that depend on the values of the other predictors, so perhaps you include interactions among those predictors. As you go down this path, you can quickly end up with a scenario where you have a model with only a small number of observations available for training, yet you have maybe dozens or hundreds of coefficients that you'd like to estimate in that model. This is a recipe for overfitting. Very easily you can end up estimating coefficients that fit really well to the patterns that exist in the training set, but perhaps don't generalize well to new cases. Regularized regression solves this problem in an automatic way. It makes us default to the assumption that our coefficients should be in some sense near zero. And we only move away from estimates near zero to the degree that we have lots of evidence that suggests the coefficients should be farther from zero. Now there are various versions of this that we'll get into as we go through the code. We'll be using regularized regression using the glmnet package in R, and here's a link to a documentation page from the folks who made the package that tell how it works. So let's go ahead and get started. So over here, I'm going to begin by loading the packages that we'll be using today and loading the data sets that we'll be studying. Okay, so the first step whenever you start working with a new package is to go to the help files. So when I go to the help files, I can see how to fit GLM with lasso or elastic net regularization. In particular, there are two key arguments to this model fitting function. This is the X argument and the Y argument. Here, X is a matrix of predictors, and Y is a vector of outcome values. In the past, we've worked with functions where you pass a model formula in that tells it the outcome and the predictors and how we think they're related. So this is one step removed from a model formula. We'll use a model formula to create this matrix of predictors X. So let's see an example here. So as one example, we're going to create the matrix X, and here I'm going to exclude an intercept because glmnet will include an intercept for us when we actually fit the model. Then I tell it I want to have two predictors in this model matrix. This is parents' log income and grandparents' log income. I tell R that I want those entered additively, and I tell it that I want to use the learning data frame to look for those variables. So if we see what we have here, this function is just going to create a matrix for us where each row is a person and each column is a predictor value. The matrix will have all numeric values, so if one of these variables was a factor, it would get spread across multiple columns coded by indicator variables 0 or 1. Okay, so we've got our predictor matrix. Then we want to get our outcome vector. So let's call this build a predictor matrix, and then get an outcome vector. Okay, so we're going to look in the learning data frame, and we're going to pull out the variable G3 log income, which is the respondent's log income that we're trying to predict in this class exercise. So if you go ahead and run that, we'll see now that Y is a numeric vector that has the log incomes of the cases in the learning set. The next step is to fit the glmnet model. So in this case, we're going to fit a lasso regression first. I'll explain lasso in a second, but first I want to show you how easy it is to fit. So here we're going to call glmnet with the predictor matrix X and the outcome Y, and it's going to create a fit object. And like you can with many R objects, you can do summary fit and you get some information about it. You can play with this object to get lots of info that comes from the GLMNet fit. Okay, what did we just do? By default, this model is a lasso regression. A lasso regression minimizes this loss function. A loss function is the thing that we're trying to make as small as possible when we're choosing which coefficients to estimate. So there's lots of betas we could pick, and we're going to pick one set of them and call them beta hat, our estimates. In this case, beta hat is going to be the argument. So beta tilde is a set of candidate coefficient estimates. And we're going to look for the argument that minimizes this whole loss function across the possible values of beta. The first part of the loss function will look familiar to you. So this is the average value, so 1 over n times the sum over all units I, of the true outcome minus the predicted outcome squared. So this here is just the training sample mean squared error. In ordinary least squares, this is the entire loss function. OLS does everything it can to choose beta hat values that minimize the squared error, thus ordinary least squares. What's different in a lasso regression is that there's this second penalty term. This penalty term has a numeric scalar lambda. This is a tuning parameter times the sum of the absolute values of the coefficients. So in short, the model prefers to have coefficients that are smaller or closer to 0, because if the coefficients are closer to 0, this penalty term will be smaller. So simultaneously, the model's trying to make the squared errors small and also trying to make the coefficients small. And in some cases, it's willing to accept a little bit more squared error in order to have coefficients that are closer to 0. The reason for this is because we think the coefficients ought to be closer to 0, and we don't want them to vary a lot sample to sample. So this helps reduce the chance that there's one sample where you just happen to get really big relationships and the beta would be really huge, but that's really just due to the idiosyncrasies of the sample. We can then look at the estimates that result as a function of this penalty parameter lambda. So here I'm showing you the coefficient on parent log income in red and grandparent log income in blue. And we see that the estimated coefficients at the far left, when lambda is 0, those are about the coefficients you would estimate if you just did an ordinary least squares model. Because after all, if lambda was exactly 0, this would equal ordinary least squares. As lambda increases, we increasingly are worried about this penalty term, and so the model is going to accept some squared prediction error in order to get those coefficients closer to 0. We see that both the coefficient on parent log income and on grandparent log income go down as you increase the penalty term lambda. In fact, when you get up near 0.1, the coefficient on grandparent log income becomes 0 exactly. By the time you get up to lambda equals 0.3, the model's going to estimate both coefficients to be 0. Effectively, for every person, it's just going to predict the mean outcome among all the people in the training set and ignore those predictors. So the big question becomes here, how do we choose the value of lambda? And we're going to come back to that in a few minutes after I show you the other version of the model that can be estimated in GLMNet. That version is ridge regression. In ridge regression, we don't penalize the sum of the absolute value of coefficients. Instead, we penalize the sum of the squared coefficients. And if you think about how these two compare, in ridge regression, we're penalizing the squared coefficients. So if a beta is pretty big, its squared value is going to be huge. Thus, ridge regression really heavily penalizes large coefficients. Now, if you think about a beta that's like 0.1, once you square that, that's 0.01. So coefficients that are near 0 contribute almost nothing to the ridge penalty, whereas coefficients that are large contribute a lot. For this reason, ridge regression is going to really pull down the large coefficients, and it's going to let the coefficients near 0 stay about where they are. This means that the behavior where, say, the coefficient on grandparents' log income fell exactly to 0 in lasso, that doesn't happen in ridge. In ridge, all the coefficients are going to end up being non-zero. They're just all going to be pulled down toward 0. So if we want to fit ridge regression, we simply do the same kind of model here, and we add the option alpha equals 0. Otherwise, it works pretty much the same. And this package actually allows you to use elastic net, which is a weighted combination of lasso regression and ridge regression if you want to penalize both the sum of the absolute value of coefficients and the sum of the squared coefficients. Here's what the estimates look like in ridge regression. So as before, as the penalty grows, those coefficients get pulled down towards 0. At the very beginning, the coefficient on grandparent log income actually goes up a little bit as the coefficient on parent income comes down. And this happens often in regularized regression when you have two predictors that are highly correlated, where as you increase the penalty, one of them might come down enough that another coefficient might go up a bit. But on the whole, what happens as the penalty rises is that those coefficients go towards 0. In the case of ridge regression, they asymptote towards 0 and never actually quite hit 0, whereas in lasso regression, they drop out of the model entirely. Okay, so the reason we're doing all this is not because we want to fit a model with two predictors. In that case, you can basically always just use ordinary least squares. Here we want to do this when we have many candidate predictors. So let's get back to that example I opened with, where you want to include lots of predictors and you want them to interact. Okay, so we're going to start with a model formula here. And this formula is hard to read because it was on too long a line. Okay, so our model formula is going to have no intercept as before, because GLMNet will add the intercept for us. Then we're including parents and grandparents' log income, and we're assuming that the relationship between those predictors and the outcome might be different in every subpopulation defined by the respondent's education, race, and sex. This is a ton of interactions, so we're going to go ahead and make this model formula and build the model matrix. And if we look at the dimension of x, we see that we have our 1,365 observations. Those are rows of the model matrix. And we have 72 columns. So once you do these interactions, it quickly explodes to a place where you're estimating a ton of coefficients. Now, estimating 72 coefficients with just over 1,000 data points, you're starting to be in the territory where you're at a high risk of overfitting to the training data, and you've got to really worry about some of these problems. So we can address this using GLMNet, where we'll automatically regularize those coefficients towards 0. I said I was going to come back to the question of how much to regularize. There is an easy way to resolve this question, and that's the cv.glmnet function. So I'm going to do that here. So here I'm creating a new fit object, and in it I'm storing the outcome of a call to cv.glmnet. cv.glmnet conducts cross-validation. At its core, cross-validation is the same as this idea we discussed in sample splitting. So in sample splitting, we said we should take our learning set and split it into two parts, a train set and a test set. Then we estimate models in the train set and see how well they perform in the test set. Cross-validation generalizes this idea by saying we could first do that like this, and then we could swap the roles of the train and test set. Use what's currently labeled train as the test set, and use what's labeled as test as the train set. You can see how this would allow us to gain efficiency because now every observation at some point is used as the training and sometimes is used as the test. Further, cross-validation is often conducted with 5 folds. So we would use 4/5 of the data for training and only 1/5 for testing. The advantage of that is that our training set is similar in size to the full learning set in which we would ultimately go on to estimate the predictions. So you can totally code cross-validation yourself, but you don't have to in this case because the cv.glmnet will do that for you internally. So let's come back over here to our course page for today. And we have our cv.glmnet function. So cv.glmnet comes with a plotting function. So we can then say plot fit, and we're going to get, this is the same plot you have on the course page. We can look at it over here. Okay, so what have we got? On the x-axis, we have log of lambda. So remember, when lambda is bigger, we are penalizing the coefficients a lot. We're pulling them far towards 0. Over here, we have small values of lambda. Then on the y-axis, we have the cross-validated mean squared error. So this is how well our model performs when predicting cases out of sample. In this plot, we can see a pattern that's common across lots of these plots. When lambda is really small, we're effectively estimating OLS. Then we have fairly large mean squared error. As lambda grows, the mean squared error falls, so we're avoiding that overfitting problem. But then there comes a point when we have too much lambda. We're like pulling those coefficients way down towards 0 and not allowing the data to speak. Between these two extremes is a sweet spot. So here is the value that minimizes the out-of-sample mean squared error. And over here we have one standard error of the estimate of lambda above that value. And there are rules of thumb that say you should pick this as your value of lambda or this as your value of lambda. Today we're just going to use the one that minimizes mean squared error because that seems the simplest, but there are good arguments for using the other one also. So to do that, we maybe now want to predict for the holdout set. Before we do that, one caveat. You can type coef to look at the coefficients of the fitted model. Before I show you what happens here, recall that lasso has the property that it shrinks many of the estimated coefficients all the way to 0. So we're about to look at the coefficients. Remember, there were 72 candidate predictors that went into the model. And when we look at them here, a lot of them are now represented by a dot. Those coefficients have been shrunk exactly to 0. And the non-dot coefficients are the ones that continue to be estimated with non-zero values. So overall, very few of these are non-zero. In fact, we can look at the total by looking at the sum of how many of these are greater than 0. We see that we started with 72 predictors in the model. We ended up with a model that has 12 non-zero coefficients. So this is a property of lasso that it leads us to a parsimonious model where only a few predictors enter that prediction. Okay, the last step is we've now chosen a model. We decided to estimate this lasso regression. We chose the penalty term lambda, and now we want to make our predictions in the holdout set. In order to do that, we can make a model matrix in the holdout set. And this is just going to use that same formula of predictors we just used, but it's going to make it using the cases that are available in the data frame holdout public. And then we can make predictions. So y hat holdout is going to be the predicted values in the holdout set, which are predictions from the model fit using the new X matrix X holdout. And we're going to make those predictions at the lambda value that minimizes the cross-validated mean squared error. So we can go ahead and make those. And if you look at this, you'll see that y hat holdout here is a matrix. It's a really tall matrix. Let's do head y hat holdout. Great, so it tells us that these are the predictions when lambda is set to that value lambda min that minimizes the out-of-sample mean squared error. And if we wanted a standard vector, we could just do y hat holdout. Square brackets tell us to go within a matrix. The comma tells us that we're having rows here and columns here. We might want to pull out that column that has lambda min. And now we're back to a vector of values, and you could stick this into your holdout data frame, build a submission, and in this case, submit those predictions to the course website if this is the approach you want to use to predict the outcomes. So that's the scoop on regularized regression. GLMNet is a fantastic package that makes this super easy to do. And in many ways, if you want to estimate an ordinary least squares model, you want to throw lots of coefficients into that model and perhaps some interactions, then you might want to consider regularized regression, either lasso or ridge, to make sure that you don't have so many parameters that you end up fitting the training data closely and generalizing poorly.